And so we call this an equilibrium. Because eventually it sort of balances, right? For every particular acid, there comes a point at which the number or the concentration of HF is stable in a solution. The concentration of H plus is stable. The concentration of F minus is stable. And so there's, the molecules are still changing back and forth, but the concentration of those three species doesn't change.
I'm kind of confused what you mean by like how they go back and forth. Like, can you explain that?
Sure, absolutely. So when we first put our HF in water, right, it's all HF and it's all together. As it dissociates in the water, as it interacts with the water, it might break up into H plus and F minus. Right? So now instead of just a single HF molecule, imagine there's a billion of them, right? And let's say, for example, I don't know off the top of my head, but let's say that 10% of them actually dissolve. It's a weak electrolyte. Only 10% of them dissociate into H plus and F minus. And so of that billion, 100 million of them are actually apart, right? But if a positive and a negative find each other, they might stick back together, right? But because there's so many of them, if one pair sticks back together, there's another pair somewhere that's breaking apart, right? And so that H and that F might find each other again and become HF, or if it's HF, it might split apart into H plus and F minus, right? We might have a little bit of each going on. And so if it's equilibrium, what we say is that those concentrations aren't changing, but at every point, there are some that are splitting and some that are getting back together. Does that make sense, May?
Yeah, okay, thank you.
Yeah. In a strong acid, it's good to sort of point this out while we're talking about it. In a strong acid, we might have an NO3 minus and an H plus that find each other and stick together, but they're going to only stick together for a short amount of time, right? We're talking maybe nanoseconds or even shorter, because it's a strong electrolyte, and as soon as it's together, it's going to break back apart, right? For a weak electrolyte like HF, they might find each other and then hang out for another minute or two before they break back apart. Strong bases are something that we should know as well. Remember that hydroxides, in our solubility rules, hydroxides are pretty insoluble. They're only soluble with alkali metals, and with that barium was the exception. And so the strong bases, let me see if I can find a little place here to put this. Strong bases are the alkali metal hydroxides. Right? So lithium hydroxide, sodium hydroxide, potassium hydroxide, that whole first group, those are our strong bases, right? And of course, just like in our solubility rules, there was that exception, barium hydroxide. Barium hydroxide is also a strong base. And again, that's because they're soluble. They dissolve completely and dissociate when we put them in solution. Okay. All right, so more than just identifying acids and bases, and last time we talked about conjugate acids and conjugate bases, more than just doing that, we need to do a little bit of being able to make sure you understand this, and then we're going to do some math with these. Right? So we're going to classify it as a Bronsted acid or a Bronsted base. Quick review, a Bronsted acid does what?
Gives up a proton.
Yeah, acid donates a proton. And the base is where that proton goes, and so we say a base accepts. All right, so how about HBr? Is he going to behave like an acid or like a base?
Acid.
Yep, absolutely. HBr is going to be an acid. How do we know? Well, he's got a hydrogen there to give up. Right? Lots of molecules have hydrogen, right? Not all hydrogens are acidic, but we usually write acidic protons, acidic hydrogens, at the beginning of a molecule, right? Either at the very beginning or at the very end. I'll talk about that in just a minute. How about NO2 minus? Does he have any protons to give up? Nope. And so he's going to be able to accept a proton. We'll call him a base. Right. How about HCO3? This is our bicarbonate anion.
Base.
He's a base because he has this negative charge, right? So he can accept a positive proton. But also he has a proton here. And so he can be an acid. And so we call this guy, he can be either an acid or a base. And we call him amphiprotic. And so he can either donate or accept a proton, and so he can act either as an acid or a base. There's another term that's very similar to amphiprotic called amphoteric. These are really almost interchangeable unless you're looking at very fine examples. Amphiprotic means it can accept or donate a proton. Amphoteric means it can act as either an acid or a base, right? And so for this particular example, those are the same thing. There is a class of acids and bases that don't involve protons at all. Those are called Lewis acids and bases, if you've heard of those. And so those are amphoteric without being amphiprotic, right? So that's a distinction that I just want to mention, but that I'm not going to ask you to know. And so this guy can either be a base or an acid. If we wanted to write an equation, just real quick, HCO3 minus could add a proton to become H2CO3, and HCO3 minus could lose a proton to become CO3 2 minus. Right? Both of those are reasonable reactions. Again, just a quick review. What's going to happen to this compound when it's in water?
It completely disassociates, right?
So it is completely soluble and disassociates. Yeah, that's from our solubility table. But with carbonates and acid, there was a special reaction that took place. We're going to get a gas out of him. Carbonates react with acid and give us what?
Is it CO2 and water?
That's it. We're going to get carbon dioxide and H2O. This is actually the system that our bodies use to regulate the pH of our blood. Bicarbonate is it's called a buffer in our blood, and it can either add excess protons to become more acidic, to soak up some acidity in the blood, or it can give up its proton to make blood more acidic. Right? This is why if we suffocate with CO2, it's very painful for us, because CO2 and water can also react to form this acid. And so the pH of our blood drops if we suffocate with too much CO2. And so our bodies freak out because blood pH is something that is related to a lot of muscular activity. If you suffocate with nitrogen, however, your body doesn't really know. Nitrogen doesn't change anything physiologically about the body, except there's just no oxygen in our hemoglobin. And so you die very peacefully if you suffocate from nitrogen. If you ever would like to kill someone peacefully, do it with nitrogen, not carbon dioxide. Okay. All right, so how do acids and bases react, right? They react with neutralization. We say, acid base neutralize one another. And so the general form of a reaction between the two is, I'm going to use the color coordination that the textbook uses, just that if you go look at the ebook, you can maybe follow along a little bit. An acid plus a base will give us some kind of salt and water. Right? Now, here's a good point to mention, that when we talk about salt, rarely do we really mean table salt, NaCl. Salt is just an ionic compound that's relatively soluble in water. It doesn't have to be. There are insoluble salts, but generally speaking, salt is an ionic compound. And so let's say that we have an acid. I'm just going to stick here. We have an acid, HNO3, and we have a base, KOH. It's going to react. We've done this kind of double displacement reaction before, right? We're just going to trade partners. If we trade positive ions, what's our salt going to be?
Potassium nitrate.
That's it, KNO3, potassium nitrate, and water, H2O. And so I'm going to highlight here our water, right, and our salt. Okay. There are times, and acid base is one of them, where it's okay to think about water as HOH, right? That's H2O, but it's sort of easier to see where those come from if you leave it as an H from the acid and an OH from the base. Right? So if you want to write your water like that in acid-base reactions, that is A-OK. If we were going to go one step further and we were going to write a net ionic equation, so this would be the molecular. Right? We talked on Friday about net ionic equations. Well, NO3 minus, that's always soluble. K plus, that's always soluble. And so our KNO3 is going to be aqueous. These are going to be aqueous. And water's what?
Liquid.
Yeah, water's a liquid. Right? I tend to put a script L for liquid. I'm not sure why, but that's what I tend to do. The potassium nitrate is going to be our spectator ions, and so we end up with H plus OH minus goes to form H2O liquid. I can quickly determine that the K plus and the NO3 minus are going to be spectator ions because the compounds with NO3 minus and K are aqueous on the left, and the compounds with NO3 minus and K are aqueous on the right. And so those are going to be my spectator ions. And so the net ionic equation is going to be the formation of water for all strong acid, strong base reactions. Right.
So if we ever have like a strong acid, strong base reaction, that's always going to be the net ionic.
Right, absolutely. And again, part of the reason that strong acids are strong is because they're totally soluble. And so whatever salt you make when you have a strong acid, strong base reaction, that salt is going to be totally soluble as well, right? That's why we know that the salt will not be a precipitate. Okay. All right. So molecular ionic and net ionic for each of the following acid-base reactions. Let's do one together, and then you can do another one later on your own. Hydrobromic acid. Let's see. I'm just going to go across my screen here. Ashlyn, hydrobromic acid. What's that one?
HBr.
HBr. Rahi, what's the formula for barium hydroxide?
BA O2, I mean OH2.
Yeah, you need OH twice. Vanya, give me one of the products that's not water.
Barium bromide.
Barium bromide, BaBr2. Right. And so we could do this equation a couple ways, right? Barium bromide, how did I know that that was soluble salt? Why did I put aqueous instead of solid? Barium's a 2+, bromide's a 1-, so I can't use my 1 and 1 trick. I can't use my 2 and 2 trick either, right? And so there's a couple ways to know this. The first is to know those solubility rules, right? Halides are in the soluble column unless they're paired with silver or lead, right? Barium is neither silver nor lead, so those halides should be soluble. The other way is to know my strong acids, strong bases. We know that HBr is a strong acid. It's on our strong acid list. Barium hydroxide, one of those on our strong base list. And so because both of those are strong, we know that this salt is going to be totally soluble. And so we end up with H plus OH minus gives us water. You get the same net ionic reaction for the second one, right? Sulfuric acid, one of our strong acids. Potassium hydroxide, one of our strong bases. This one has a wrench in the works though, because, well, let me go back up here. We need to balance. We need 2 here and 2 there. This one's similar because this is H2SO4, so it has 2 protons, and potassium hydroxide, KOH.
Dr. Davis,
Yes.
I think, doesn't the 2 go in front of the water, not the barium bromide?
Yes, you're right. You're right. Thanks. Yep. Okay. So we talked a little bit about this last time, reactions that give us a gas product. Again, those are going to be carbonates. And usually these carbonates are weak bases. And so we will have some salt left over usually. And so let's see here. If we have HCl reacting with sodium carbonate, CO3. These are both aqueous. Right. What are my products going to be?
Sodium chloride, water, and carbon dioxide.
Yeah, so NaCl, aqueous. And again, I'm just going to write it this way so that you see the process. Let's see if I can clean up my handwriting a little bit. Right. We need to balance this. So let's put a 2 here and a 2 there. Right. So Beard was absolutely right. Really, we can just ignore this piece because it's going to break down into water and carbon dioxide. Our net ionic equation has 2 products now. This is a liquid. He's not going to be ionized. This is a gas. He's not going to be ionized. But Na and Cl will be. So you end up with 2H plus CO3 2 minus give us H2O plus CO2. Again, remember ions don't need the aqueous because in order to be an ion, it's got to be dissolved in solution. But if it's either together as solid, a precipitate, or a liquid, or a gas, what we consider pure compounds rather than dissolved and dissociated, then it does need a state symbol.
How did you know that it was going to break into the H2O and CO2?
So carbonates are very good at this because the carbon dioxide really wants to get out of that carbonate. And really, you just have to know this part in purple. Right? If you have H2CO3, this is called carbonic acid. If you have H2CO3 and it's in water, it's in a solution reaction, it's always going to break down to form water and CO2.
Okay, thank you.
Yeah, that's the same one we saw on Friday. And anytime you talk about gas producing acid and base neutralization, it's the example that they give. Okay. So for now, our sort of introduction to gases, to acids and bases, that's where we'll stop. And so the third type of solution reaction is an oxidation reduction or redox. I don't know why we switch them when we do the abbreviated version, but we talked about precipitation reactions on Friday, acid base, and redox today. All right. So in an oxidation reduction reaction, really what we're doing, what we're looking at is electron transfer. So if we were to react magnesium as a solid with oxygen, that's a gas. What's the formula for magnesium oxide?
MgO, Mg2O, or is it just MgO?
Just MgO. Magnesium's a 2+, oxygen's a 2-. We end up with MgO. It's a solid. So we need to balance this. Let's see, 2 there and 2 there. But what's happening between our products and our reactants? Well, magnesium, when magnesium is just by itself, does it have a charge?
2+.
So when it's just magnesium and I'm digging it out of the ground and it's a pure block of magnesium, he doesn't have a charge, right? He's just what we call neutral. And so over here, he's neutral. We sometimes indicate that with a little superscript 0, right? Just like we write the superscript charge for an ion. If it's a neutral, we put a 0 there just to remind us that he doesn't have a charge. Okay. But now you can answer, Baird. In magnesium oxide, what's the charge on magnesium?
2+.
Yeah, for sure, 2+. And so what has happened between reactants and products is that he loses 2 electrons per magnesium atom, right? Well, oxygen, when it's in its molecular form, doesn't have a charge, right? We don't write one there. So we can put a little 0 to show that he's neutral. The charge of oxygen in an ion, Rosie?
2-.
2-. And so from here to here, right, oxygen gains 2 electrons per oxygen atom. Right? And so overall for this reaction, how many electrons are transferred? Taylor?
0.
So net, there's 0 charge change, that's true. But how many are transferred? If the magnesium loses 2 per magnesium atom and the oxygen gains 2 per oxygen atom, how many electrons are changing hands?
4.
4, that's right. So this is a 4 electron reaction. Right? We have 4 electrons going from the magnesium, 4 electrons going from magnesium atoms to oxygen atoms.
Why is oxygen's charge on the reactant side 0? Why is it not like -2 already?
Because it's not an ion yet, right? It has all the electrons it started with. It hasn't gained or lost any, right? On the periodic table, those elements, if they have, so oxygen's atomic number is 8. And so if oxygen starts with 8 electrons, he doesn't have any extra, any fewer, and so he has a 0 charge. Oxygen only gains a charge when he starts reacting with other things.
Okay, thank you.
Sure. Another way that we can think about this is to break it down into what they call half reactions. I don't want to go too deeply into this, but we could have 2 Mgs go to 2 Mg2 plus 4 electrons, right? Our charge is balanced. I've got no charge on the left. I have 4 positive charges and 4 negative charges on the right, so there's net 0 charge. O2 plus 4 electrons gives me 2 O2 minus. Again, my net charge is 0. I've got 4 negatives on the left, and 2 times -2, that's 4 negatives on the right. When we add these 2 reactions together, my 4 electrons cancel out. I don't have any electrons left over at the beginning or the end. They're just transferred, and we end up with this 2. Well, we end up with our overall reaction, right? 2 Mg plus O2 gives us MgO. Okay. The reason we call this oxidation reduction is because we're looking at sort of what's happening to the charge of these atoms to ions. Right? If we look at the magnesium increases in charge, right? And so we say that it is oxidized. Don't know where my O went. Magnesium is oxidized and oxygen is reduced. Okay. If we look at the oxygen charge, that one's easier to see. It goes from a 0 charge to a -2. That's lower, right? That's reduced. The oxidized, we don't call it increased. And so that one's a little bit harder to associate. But if we increase our charge, we're being oxidized. Another way to think about this is the oxidation is the loss of electrons, right? And we can think about reduction as being the gain of electrons. And so maybe you've seen this before, but oops. Why are you not changing color? Well, I don't know. But oxidation is loss, reduction is gain. If you can remember oil rig, you can remember that one. Another one I like, just to give you one more here. If we lose electrons, that's oxidation. If we gain electrons, that's reduction. Leo, the lion, goes grrr. Right. So whichever of those is easier for you to remember. Oxidation is whenever we lose an electron. Reduction is when we gain it. Okay. So if we were to look at this reaction between zinc and copper sulfate, zinc here, oops, zinc here has a charge of what?
0.
0, absolutely. What about zinc on the other side?
2 plus.
2 plus. How about copper on the left?
2 plus.
2 plus. And copper on the right?
0.
0.
Well,
Yeah. Because sulfate is sulfate on both sides, the charge isn't changing, right? If sulfate broke down into something else, then we'd have to worry about it. But because sulfate because sulfate doesn't change, we're just going to leave him be, right? We don't really care much about the sulfate here. So, what happened to our zinc? Did he gain or lose electrons?
Lost.
He lost electrons. And I'm sorry, I can't change my pen color. I don't know what happened here. But anyway, copper, what's copper doing?
gain 2 electrons.
That's right. And so zinc was oxidized or reduced?
Oxidized.
Oxidized. Copper then must have been reduced. Because zinc was oxidized, that means that the process of him being oxidized caused something else to be reduced, right? In this case, it was the copper. And so the zinc oxidation process made the copper get reduced. And so the agent of that reduction, the thing that caused that reduction to occur is the zinc. And so we call zinc a reducing agent. And vice versa, copper is our oxidizing agent. Right? Those seem a little bit backwards, but just think about it as the thing that does the oxidation to another compound is the oxidizing agent. And so the copper oxidizes zinc. And so the copper is the oxidizing agent. Zinc reduces copper. Zinc is the reducing agent, even though in the process, zinc gets oxidized. Okay. So being able to sort of identify what's being oxidized, what's being reduced, and then identifying oxidizing agents and reducing agents is a big part of this week's Alex. What I've written up here, we call these oxidation numbers. And I want to walk you through some rules for calculating oxidation numbers. And that's where we'll end for today. But there are some rules in sort of determining what the oxidation number is for an element. Notice that I put an oxidation number on copper alone, not on all of copper sulfate, right? Each element in your equation, each element in your chemical reaction gets its own oxidation number. So let's look at some oxidation number rules. The first is that free elements, right? That's elements that haven't combined with other elements. That includes O2, H2, all the diatomics are part of this. And so free elements, in other words, elements by themselves, have an oxidation number, I'm going to abbreviate that ON throughout this rule set, of 0. They have exactly the number of electrons they came into the world with, right? They don't have an overall charge, and so their oxidation number is 0. If we have an ion, so lithium plus, aluminum 3 plus, sulfur 2 minus, if we have a monatomic ion, right, so one atom, monatomic ion, the oxidation number equals whatever the ion charge is. Put in parentheses here, N plus, 2 minus. And so whatever the charge is on that ion, that's the oxidation number of that compound, of that species. Oxygen in particular, whenever it appears, aside from being a free element, is usually -2. Right? For oxygen, the oxidation number is usually -2. The only time that we'll see it there's not -2 is in hydrogen peroxide, H2O2. The oxidation number is -1. That's a pretty common exception. I'm sure it'll show up in Alex. and maybe even on a quest next week. Sorry, this week on Thursday. And so oxygen usually -2, only in hydrogen peroxide for us only, is at -1. Okay. Hydrogen is usually +1. Right? And for us in this class, it will always be +1. There are a class of compounds called hydrides. The IDE should tell you that hydrogen has a negative charge in those compounds. And in those, hydrogen is -1 instead of +1. But we will not play with any hydrides in this class, and so you don't have to worry about it. The alkali metals, right? Remember that's group 1. Their oxidation number is always +1. Alkaline earths, that's group 2. Oxidation number is +2. Fluorine, not all of the halogens, but just fluorine, has an oxidation number of -1. Okay. And the last rule here is not a specific oxidation number rule, but the sum of all oxidation numbers equals the overall charge on the compound or the ion. Okay. I know it's 12:20, but let's do, with this information, right, let's go back and do sulfate. Oxygen always -2, so we're going to put it there, right? And it tells us that for the charge on any ion has to equal the sum of the oxidation numbers. So SO4 is a 2- thing. And so if oxygen has an oxidation number of -2, sulfur has to balance it out, so we end up with 2-. There's 4 of those oxygen atoms, so that's a -8 there. What does sulfur have to be in order to make it overall -2?
+6.
6.
Yeah, +6. And so the oxidation number for sulfur in sulfates is +6. All right. There's practice with oxidation numbers and things in Alex. I will go ahead and update Alex to stop here at oxidation numbers. And so that is what is due tomorrow at midnight. All right.
Dr. Davis,
Yes.
could you please go back to the last slide? I didn't really catch the last part of the notes.
Sure. Yeah, and just
Thank
a
you.
reminder that all of these lectures are recorded and uploaded, and the links are on Moodle if you ever need to go back.
I appreciate that. Thank you.
Yes, sir.
Thank you.
All right, y'all have a good one. Sorry I kept you a little long.
Thank you.
Thank you.
Thank you so much.
Thank you. I got it now.
Sure.
Have a fantastic day. Thank you.
Thanks. Bye-bye.
Bye.